In this video, I'm going to discuss how to utilize SPSS in order to evaluate a distribution for normality. Before we get into the how-tos with SPSS, I want to talk a little bit about the characteristics of a normal distribution and what kinds of aspects of your distribution we're looking for in making that assessment of normality or lack thereof. First off, our variable x is assumed to be continuous, and so by virtue of that variable being continuous, we would expect the distribution to be reasonably smooth. Secondly, we make the assumption that our distribution of scores is unimodal. So then third, that it's symmetric around the mean. And what I mean by that is at the center of the distribution we have the mean, median, and mode, and essentially we have symmetry around that. So in other words, we don't have skewness in the data, but rather in particular when we're looking at the percentage of scores falling at or below or above the mean, we would expect it to be 50%. And essentially what that translates into is that the mean and median are falling at the same location. We expect our distribution to be bell-shaped, as we see right here, and that the curve is asymptotic, meaning that technically speaking we make the assumption that the tails, as we move out into the tails on our variable, that they actually continue getting closer and closer to the x-axis but never actually touching it. Also, there's a fixed relationship between the standard deviation and the area underneath the curve. Now, in particular, when we're looking at the issue of whether our data are skewed, or whether or not our data are skewed, are normal, one dimension that we want to look at is the issue of skew, and this pertains to that issue of symmetry. So when our data are not symmetric, what that translates into is that the mean, median, and mode are not falling right at the center of the distribution, as we saw previously. As I mentioned right here, the mean, median, mode all fall at this point right in the center, and you can see that the extreme scores in the tails are sort of balancing out so that really those three indices are all falling at the same point. When we're dealing with skew, though, what happens is that we have extreme scores perhaps in the lower tail or the upper tail, and essentially they're not being offset by scores falling kind of at equal distances from the mean. And so that translates into the mean being pulled in the direction of those extreme scores, so like as such. So then the mean, median, mode actually are not all falling at the same point within the distribution. So when we talk about skew, we can talk in terms of a negative skew in the data, and so a negatively skewed distribution really has that skew kind of pulling in terms of the lower tail. So you can see that we have some extreme scores. They're falling a little further out here and less so in the upper tail. And so you can see that the mean is being pulled in that direction. And so the data is skewed negatively. If we're talking about positively skewed data, then the more extreme scores are falling in the upper tail, and you can see that skew is kind of in this direction. So that's an example of a positively skewed distribution. All right, so that's and so again, the issue of skewness bears on that dimension that we were talking about with respect to the symmetry of the distribution. And so you can see that with skewed distributions we can have our symmetry becomes off. Just keep in mind that skewness, these are sort of more idealized notions. We could have even more radically skewed distributions or less skewed distributions, but these are just sort of to represent the basic ideas behind skew. In terms of kurtosis, it's a little trickier. A lot of times folks kind of discuss kurtosis in terms of how peaked the distribution is. It's really kind of a matter of how peaked the distribution is in relation to how the tailedness of the distribution. So let me start off. Here's a normal distribution, and we can call this distribution mesocurtic. So essentially this would be an example of a normal distribution. And then let's say we take our normal distribution, and I'm going to overlay a leptokurtic distribution. And essentially what we have right here are thicker tails that you can see at this point right here it would overlap with the normal distribution. Same over here, and so we have thicker tails and we have more peak at the center of the distribution. So that's what's called a leptokurtic distribution, and then a platykurtic distribution is more rectangular. And you can see right here that our tails are thinner, and you can see that we end up having a number of scores exhibiting similar frequencies, and then sort of trailing off in this kind of manner. So that's more of a platykurtic distribution. So you can see that, like I said, kurtosis really bears on, it's not just a matter of how peaked or flat a distribution is, but it also pertains to the tailness of a distribution. And there was a really great article written in 1997 by DiCarlo, where he lays out this particular discussion. So it's really, it's something that I would definitely check out. It's a really good discussion of kurtosis. So when we're assessing normality, then we have to keep in mind these two dimensions, and we also want to keep in mind that a distribution can deviate somewhat from normality or considerably from normality, and so we have to keep in mind that there's no you'll never have a perfect data distribution where it's going to be perfectly normal. It just is not going to happen. So you have to think about normality as an ideal that we are really striving for. And a lot of our statistical techniques make the assumption that distributions are normal in shape. But again, you may never have perfect normality, but the real ideal is to try to find to determine whether or not the distribution is close enough to normality that it's workable. So at any rate, let's now transition to looking at SPSS. So one way in which we can assess for normality using SPSS is to use the Explore option. And basically, if we just go through the Analyze, Descriptive Statistics, and Explore, we can generate information that bears on our assessment of normality. So I'm going to open up SPSS and kind of show you what I'm talking about. So we have two variables in the data set. I have achieve and I have interest. And I'm going to focus right now on the achieve variable. And essentially, to utilize the Explore option, we're going to go to Analyze, Descriptive Statistics, then go to Explore. We'll move the variable achieve over to the dependent list, and then under Statistics, we could ask for a few things. We have descriptives, we have confidence interval if we want a confidence interval around the mean. We could ask for outliers, but right now it's a little trickier. I mean, we can identify potential candidates as outliers. Well, I'll go ahead and just click on that, and I'll show you what I mean. We'll click on Continue. Under Plots, we'll ask for a histogram, and then we'll ask for normal plots with tests. Next, we'll click on Continue, and then on OK. And so now you can see in terms of the descriptives, various pieces of output. So we have our sample mean right here. There's our confidence interval, 95% confidence interval is right here. You can see the median is 49.5542. So you can actually see that the mean and median are pretty close together. So there's not a lot of difference there, which would be more consistent with normality. Then we have a couple of indices. We have a skewness statistic and we have a kurtosis statistic. And so these are the values for those two statistics. And so one way that we can assess for normality is to look at these two indices and determine how much skew and kurtosis there is. And there are various rules of thumb for making judgments about the level of skew and kurtosis. I'm going to stick with sort of a rule of thumb that is laid out in textbook values on skew, where they talk about rules of thumb, and basically they suggest, first of all, these two indices are scaled where 0 would reflect either 0 skew or 0 kurtosis, meaning for kurtosis that would be mesokurtic distribution. A positive value would indicate either positive skew or a leptokurtic distribution if we're talking about kurtosis, and a negative value would reflect negative skew or more of a platykurtic distribution when we're talking about kurtosis. So, there are various rules of thumb. Some folks are a little bit more stringent than others. One possible rule of thumb is if your indices are falling outside of -1 to +1, then that would be a signal that we have a lack of normality. The source I use suggests, kind of as a rule of thumb, basically a -2, +2 range. And so we'll just stick with that in this particular case. So, so at any rate, you can see that, and so what we're going to assume is that as long as our indices are falling between -2 and +2, then that would be a signal that our data are reasonably consistent with normality. And that seems to be the case right here. Both of these values, it looks like we have some slight negative skew, and the distribution is slightly platykurtic, but it's not a very strong level of skew or kurtosis in the distribution. So next we'll scroll down. You can see that because I clicked on that outliers button, I get extreme values. So what it does is it's going to give you the case number and the actual raw score values within the data set. And so these, you can consider these as candidates for further evaluation for being outliers. But there's always going to be extremes in your data set, because you're going to have high and low values. So these are essentially the highest and lowest values on our variable for these individual cases. So if we want to do further follow-up and determine whether we have outliers, we could use these as sort of candidates for further evaluation. So with our test of normality, you can see right here we've got the Kolmogorov-Smirnov and Shapiro-Wilk tests. And these are significance tests, and basically the idea is that you're testing your data against the null hypothesis, which is that the distribution follows normality. So what you have right here under the sig, these are p-values, and the alternative hypothesis is essentially that your data are not following normality. So using conventional hypothesis testing logic, these p-values right here, if the p-value is less than or equal to 0.05, that's a conventional alpha level, by the way. If it's less than or equal to 0.05, then we would reject the null hypothesis and infer that our data are not following a normal distribution. If the p-value is greater than 0.05, then we would essentially make the judgment that our data are consistent with normality. The two tests, there are various rules of thumb regarding the use of these tests. What I've read is that essentially Kolmogorov-Smirnov is better utilized when you have larger sample sizes, such as greater than 50. Shapiro-Wilk is better utilized when you have smaller sample sizes, less than 50, for example. It's also kind of important to note that these tests are impacted by your sample size. And with large enough sample sizes, it is possible that you could have significant statistical significance indicating significant departure from normality, despite the fact that the data are departing in a relatively minor fashion from normality. So it is useful to use the test, but in conjunction with more graphical approaches. So a graphical approach that we can also look at is the QQ plot, and what we're looking at right here is essentially a plot of the observed values on your variable plotted against what the values that would be expected under normality. And so what we have right here is essentially a plot. This is essentially a regression line right here that's following through this, and the degree to which the data are deviating from that line, that would be an indicator that we have an absence of normality. But you can see right here the data is following pretty closely to that line, signifying that we have good evidence of normality. So you can see that using several of our indicators, the skewness and kurtosis statistics, the test of normality, and our data set actually had an n equal to 80. So we'll just kind of go with this Kolmogorov-Smirnov test right here. That was non-significant. You can see that the QQ plot is suggestive of normality. You can also look at the histogram to evaluate normality as well. And so you can see that It's not perfect by any means, but you can see that it appears to follow a relatively normal distribution. So we're going to stick with that. Then finally, we can go down to the box plot, and essentially what we're looking at, the box is actually encompassing the middle 50% of the scores in the distribution. The line in the center of the plot box right here is actually the median of the distribution. And the whiskers right here, you can see that the whiskers appear to be kind of extend equidistant from the box. By the way, the upper portion of the box right here, this edge right here is representing the 75th percentile, and the lower box or lower portion of the box edge is the 25th percentile. So essentially, if the box is sort of sitting equidistant from the whisker edges, and you have it kind of laid out where essentially the median is falling right in the center of it, that's going to be evidence of normality as well. All right, so that's kind of a demonstration using using a variable that I actually created randomly at random to simulate a normal distribution. Let's look at this variable right here, and I've actually created this variable to deviate from normality, just to give you a point of contrast. So what we'll do is we're going to go to Analyze, Descriptive Statistics, Explore. We're going to move this variable over and add in interest here. Under Statistics, we'll leave all the same things as before, the same for the plots. We'll click on OK. And so now you can see in terms of skewness, it's 2.947. So we definitely are exceeding the 2 in absolute value that we were talking about as a rule of thumb. Same goes for kurtosis. So in both of these cases, there would be evidence that we have an absence of normality. Under extreme values, you can see, again, right now it's kind of hard to identify which value would be an outlier, but I actually had set up the data set where I created an extreme or value or an outlier with case 1. So you can see it's picking up right here. This is the highest extreme value on the positive or on the high end of the distribution. In terms of normality, you can see that Kolmogorov-Smirnov test is statistically significant, suggesting that we have a significant departure from normality. If we look at the histogram, you can see there's that case that I was telling you about. So you can see where the skew is coming from in our data right there. If we scroll down, look at the normal QQ plot, you can see that for the most part the data appears to be following normality, but then we have that one case right there that appears to be deviating substantially from the regression line. So that's indicating that we have a problem in terms of an outlier. And then if we scroll down and look at the box plot, you can see that the more extreme values get an asterisk or a star, and you can see there's case 1 represented right there. So there you go. By the way, if you want to look at this particular plot a little bit more closely, we can also double click on the plot, and under Elements we can actually click on Show Data Labels, and you can see you get the case numbers associated with the observation. So you can see that observation that I was showing you right there. There's the case number 1. So kind of going back to the data set, I specifically set this up so that this case right here would be an outlier on the interest variable. Now, we could also assess for outliers by converting our raw scores into z-scores and then using sort of a rule of thumb for judging extreme scores and candidate outliers. So, for instance, if we go to Analyze, Descriptive Statistics, go to Descriptives, we'll move interest over to the Variables box and click on Save Standardized Values as Variables. We'll click on OK. And then when we go to our data set, you can see that we have z-scores. And one rule of thumb is that a case may be an outlier if the z value for that case exceeds 3. So if the absolute value of the z-score exceeds a value of 3. And so you can see that case 1, that appears to be the case, whereas as we scroll down, you can see that, there are no other cases. If we want to go a little bit further, and this is a fairly small data set, so it's easy to scroll through and see where we might have the outlier, but we could also, this can be handy if you're using a larger data set. We can use the Explore option, go through and add the z-score to the dependent list, click on OK, and if we've asked for those outliers, now we get, with the extreme values, the values that are presented are not raw score values, but actually the z values that are in the data set. So you can identify right away which case is potentially problematic. You can see under the lowest, case 68 actually has a negative 2.08376. So that's not an outlier but from a conventional standpoint using our rule of thumb, but it is one of the more extreme cases in the data set. A few other things to kind of note. We could also generate just skewness and kurtosis statistics. If we go under descriptives, I'm going to click this off. Under options, you can ask for skew and kurtosis statistics there. So just kind of scrolling down, you can see that we have the mean, standard deviation, and then the skewness values and kurtosis along with their standard errors. The same would also go if we go through the frequencies option. We could add interest right here, and under statistics we could ask for standard mean, median, and mode, standard deviation, variance range, and then over here you can see skewness and kurtosis. So if we did that, we can also get the descriptive data for that variable, and then you've got the skewness value and the kurtosis value right here. So those are just a couple of ways you can get some of the same information. I tend to find the Explore command or the Explore option the most helpful when it comes to evaluating normality, because there are just so many different components that are kind of aggregated under that option. So that concludes this video presentation.